My name is George Willis and I'm a Professor of Mathematics at the University of Newcastle. I'd like to tell you about what I do, which is the mathematics of symmetry, and how I came to do it. When I was about 12, I was interested in atoms, astronomy and prehistory. I knew the distances to all the planets, in miles at that time because Australia hadn't yet adopted the metric system. It was an exciting time. Space exploration was starting up and people were getting ready to fly to the moon. Bushwalking and fishing were other interests of mine, and I wanted to be either a fisherman or some sort of a scientist when I grew up. I wasn't very good at fishing though, and spent a lot of my time untangling fishing line, which taught me patience and persistence. I was much better at science and mathematics, and I liked learning new things. In Year 7, we started to learn about algebra and representing unknown numbers by letters. In Year 8, we learned about trigonometry, which is the mathematics used to calculate distances we can't measure, such as heights of trees and distances to planets. Learning to do new things is exhilarating, and you can keep learning and growing all your life. As a mathematician, I'm always learning to do new things which other people have discovered, and sometimes, if I'm lucky, I discover new things which I can teach to others. It's like a computer game with endless levels and worlds to explore, but whose worlds are part of the real world. Speaking of exploring, my family and I went on a caravanning holiday from Adelaide to the Snowy Mountains. In Tumut, we saw the Snowy Mountain scheme, which was new then. On Mount Kosciuszko, we saw our first snow, and in Canberra, we got lost. While wandering around Canberra, we saw this building and wondered what it was. It looked like a flying saucer to me. Years later, I learned that it is the home of the Australian Academy of Science. Later still, I was honoured to be elected a Fellow of the Academy because of new things I had discovered about the mathematics of symmetry. So what is symmetry and how do mathematicians study it? We say that something is symmetric if one part looks the same as the other parts, or if it shows a repeated pattern. Symmetry is all around us. It is useful to us and pleasing to look at. This fan is symmetric. If we rotate it through a quarter of a turn, it looks the same. This other fan is symmetric too, but under a rotation through 1/3 of a turn. And this bicycle wheel is symmetric under a rotation through any angle. This tabletop is symmetric. If we pick the table up and rotate it through half a turn and put it down again, it looks the same. This is called a rotational symmetry. It is also symmetric about a line down the middle from top to bottom, and about a line from left to right. These are called mirror symmetries or reflections. The pattern of tiles on this floor is symmetric. Not only does it look good, but the symmetric arrangement organised the work of the tiler laying the tiles. We can imagine the same pattern continuing to any floor size or even to an infinite floor. The bricks in this wall are also laid symmetrically. We also see symmetry in nature. Symmetry need not just be something that we see. Repeated patterns can appear in things that we do, such as walking, or in things that we hear, such as the beat in music, and also in the equations of mathematics and physics. These examples have different symmetries, even when they are similar. The two fans and the wheel all have rotational symmetries, but not the same rotations. The wall and the floor have different symmetries because the pattern on the floor can be rotated through a quarter turn and look the same, but that is not true for the pattern on the wall. Mathematicians can tell whether objects have the same symmetry by their symmetry group. This is an abstract idea for measuring symmetry in the same way that number is an abstract idea for measuring size. It's abstract because, just as different sets can have the same number, we might have 5 apples or $5, different patterns can have the same symmetry group. To think about the group of rotations of the fan with 4 blades, we name the rotations and see how they interact. Let's call a rotation which does nothing E. We'll call a rotation through a quarter turn A, through a half turn B, and through a 3/4 turn C. The symmetry group is an algebraic record of how these rotations interact. For example, if from the starting position E we apply a quarter turn A, followed by another quarter turn A, we write that as A plus A. The result is the same as a half turn B, and so we write A plus A equals B. Let's do the same with the symmetry group of the tabletop, which is the same as the group of this playing card.
The markings on the card are not preserved under the rotations and reflections, and we use them to keep track of the symmetries. Here is the starting position E. Let's call the rotation through a half turn A, the reflection in the line from top to bottom B, and the reflection in the line from left to right C. If, from the starting position E, we apply a reflection B in the vertical line, and then follow that with a reflection C in the horizontal line, we will write the combined operation as B plus C. The result is the same as applying a half turn, and so we write B plus C equals A. How the symmetries of the fan and of the tabletop interact is recorded in these tables. We see from the tables how the symmetry groups differ.
I'd first heard about groups at school, but not really understood them until university. As you learn more, things fit into a bigger picture. For instance, at age 12 I had read that atoms have electrons at different levels called shells, and that different shells have different numbers of electrons.
The numbers of electrons in the shells is the reason that the elements, hydrogen, helium, lithium, etc., are arranged in the periodic table. At university I learned the reason for that, and that the numbers of electrons in each shell derive from the symmetry group of a sphere.
Symmetry groups are hard to understand in numbers. In a sense, we know all the numbers. We can reach any number by starting at 0 and adding 1 over and over again. We don't know all groups in the same way. Great progress has been made in classifying symmetry though.
For example, it's been known for thousands of years that there are only 5 regular solids: the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. More recently, a complete list of all groups which may appear in physics, such as the symmetry group of a circle and a sphere, was worked out about 100 years ago. More recently still, an effort spanning more than 150 years completed the list of finite groups, such as the groups of the fans and tabletop, about 30 years ago.
Repeating patterns can also be seen in family trees.
Each person has 2 biological parents. They each have 2 parents, and so on. The symmetry groups of relationships or networks such as these are not so well understood, and they are the groups which I investigate.
I started working on them when I moved to Newcastle in 1992. A visitor from the US asked a question about diffusion, which is the process by which a smell, starting in one part of a room, spreads throughout the whole room. I thought about this problem incessantly for 2 months, like trying to untangle a really badly tangled fishing line, until a breakthrough came one day as I was walking to the university.
Here is the picture that came into my mind, although not with Tim Tams and jelly babies. This picture, more precisely, the algorithm it represents, was only halfway to solving the problem though. Many more months of work were needed to solve it and then to write down the solution, but I knew that I was on the right track after this insight. Solving this problem opened the way to understanding the symmetry groups of networks and relationships, which I and others are now exploring. And I sometimes make this sweet version of the picture to celebrate the first step.
Here are some things that you can do to explore symmetry.
Bake a cake. Share the cake with friends. To share jelly babies fairly, we count them. How do we share a cake fairly? Does the symmetry of the baking tin help to bake the cake evenly, to remove it from the tin, and to share it? What if the tin was in the shape of Australia? Calculate with the 3 rotations and 3 reflection symmetries of an equilateral triangle, as we did with the fan symmetries. Be careful, in this case different rotations result if reflections are done in a different order. Think about the symmetries of a fan. Why is it important that the fan does not have reflection symmetries? Finally, here are some search terms to use should you wish to see more about symmetry online. You don't need to look online though. You can see symmetry in the world around you. Look for it in plants, animals, rocks, and things that people make.
Symmetry is all around us, and mathematics helps us to understand how symmetry organises the patterns we see in the natural world and in our human creations.